So this is a problem from the 2018 Aime, and it says let n be the number of complex numbers z with the properties that the magnitude of z is equal to 1 and that z to the 6 factorial minus z to the 5 factorial is a real number, which just means it has an imaginary part of 0. And we're asked to find the remainder when n is divided by 1,000. So since we have that the magnitude of z is equal to 1, we know that z is just going to look like e to the I theta, right? And we can actually make a convenient substitution here. So we know that z to the 6 factorial is z to the 5 factorial times 6, which is also z to the 5 factorial to the 6th, right? So here we can just make a substitution that w is equal to z to the 5 factorial. And we're going to get that w to the 6th minus w, the imaginary part of this is equal to 0. And since w is also going to look like some form of e to the I phi, right? We get that, we can actually apply Euler's formula here. So e to the I phi is going to equal to cosine of phi plus I times the sine of phi, right? And this part is all real, right? So when we're looking in the imaginary plane or the imaginary part, this cosine term doesn't actually matter at all. It's only the sine, right? Probably shouldn't have erased that. Yeah. So that part does not matter. It's only the sine here, right? And since w to the 6th, um, so since w is equal to e to the I phi, when you raise that to the 6th, that's just going to be the same as e to the 6 phi. That's w to the 6th. And here we can apply Euler's formula, right? So sine of 6 phi, since that's the only part that matters, we're talking about the imaginary part. So sine of 6 phi minus sine of phi is equal to 0. And we can just set those equal to each other. Okay, so now we have two cases that we can look at to see what values of phi work, right? So sine of some angle alpha can equal sine of another angle beta in two cases, right? Either beta is just alpha plus some 2 pi k, right? Or beta is alpha is pi minus alpha plus some 2 pi, let's call it a different number n, right? And this makes sense because if you draw a unit circle and you have some angle alpha, obviously if you go 2 pi radians around, you're going to get to the same place, right? So that way the signs are going to be equivalent of those angles. And pi minus alpha is just basically a reflection about the y-axis, right? This is pi, and this is alpha. So pi minus alpha is going to be going alpha radians back from pi. And we notice that that way these two signs are going to be equal. Okay, so that's case one here, and we're going to assume that 6 phi is basically beta. So we're putting this into our equation that 6 phi is equal to alpha is phi plus 2 pi of k, right? Or phi is equal to 2 pi k over 5, right? And phi corresponds to the phi in w, right? E to the I phi. And since it's asking about, the question is asking about the number of complex numbers z, which is directly associated with the number of complex numbers w, we can find the number of complex numbers w and then solve for z, right? That's going to be easy. Now, since we have infinite possible angles here, you might think, you might accidentally think that um, there are infinite solutions, but you'd be mistaken because the question asks about the number of complex numbers, right? And eventually, once you go 2 pi radians around, right, even though the angle is a different number, the cosine and sine are going to be the exact same. So the complex number itself hasn't changed. right? So there are only a finite number of complex numbers possible. So with 2 pi k over 5, right, you might know this as the fifth roots of unity, right? And there are only 5 of those possible values. Um, so the fifth roots of unity are basically the solution to the equation x to the 5 minus 1 is equal to 0, right? And we know that because it's a polynomial with the degree 5, it must have 5 solutions. And to get understanding for why these are the solutions, right? And you raise that to the fifth, that is obviously going to be e to the I 2 pi, and that's just equal to 1, right? And there are only going to be 5 distinct solutions for these because they're solutions to a polynomial with degree 5. Okay, so now we know that W only has 5 possible solutions. So there are 5 solutions in case 1. So in case 2, let's look at case 2 here, is corresponding to this. So beta equals 6 pi, which is pi minus phi, or alpha, plus 2 pi n. Right, so let's just, we have 7 pi is equal to, you can factor out pi. We have 2n plus 1 and divide by 7, like so. Now, how many distinct solutions for phi do we have this way? Well, what we can actually notice is that this is equal to 2 pi n over 7 plus pi over 7, right? And this is important because we're just adding by some constant pi over 7 to the angle phi, right? So that's just going to offset the angle. But the core part that's actually changing here, the part with the variable, 2 pi n over 7, we know that this is going to be the 7th roots of unity. Like the 5th roots of unity here, solution to x to the 7 minus 1. And we know that must have 7 solutions, right? But we're just adding by a constant angle here, right? So if you imagine on the unit circle, you had all the 7 roots of unity, you're just offsetting those a little, right? So there's still only going to be 7 distinct solutions. So nothing has actually changed here from the case where they were just the 7th roots of unity. So as a total, we have 7 solutions for W in this case as well. And now to understand why this is gonna make it so much easier for us to solve for Z, we can look at, or we can think about what happens with W, right? So W is going to equal e to the I phi, and that's Z to the 5 factorial, which means e to the I phi over 5 factorial equals Z, right? So now phi has basically been, so phi you can multiply by 120, and there are now going to be 120 distinct solutions that work, right? Because you're basically subdividing the angle phi into 120, right? So let's say you have 5 solutions for W that work here. You can now multiply that by 120, and those will all work, right? So now you have 5 plus 7 times 120. So that's 12 times 120, 1440, and taken mod 1000, our answer is 440. And we are done.